Using the method of Gauss' law, determine the electric field at a point that is 2 meters from the center of a uniform ball of charge. The ball of charge has a radius of 6 meters and has a total charge of 10 coulombs. Okay. We want to begin by drawing this thing. So draw a circle. This will represent the ball, okay? And now looking at the problem, what pieces of information does it tell you? It tells you that the electric field at a point, okay, it wants to know the electric field at a point, but the point that is 2 meters from the center of the uniform ball of charge. So say this is the center point that is 2 meters from the center. Right off the bat, we're drawing our Gaussian shape, okay? So this is going to be our Gaussian shape. This is going to be where we base off everything. Now, it also says that the ball of charge, this ball, not the Gaussian shape that we draw, this whole thing, has a radius of 6 meters. So 6 meters. And a total charge of 10 coulombs. Charge is 10. Okay, so this is the pieces of information we know. Now, the 2 meters from the center of the uniform ball, with our Gaussian shape, we could identify this 2 meters as our radius. This is such a bad marker. Hold on. As our radius. Okay. And now, if this is our radius, what would that make this? This, we're just gonna call it A. Okay? Now, recall our equation to find flux. It's going to be integral of electric field vector times dA, so surface area. So we're deriving these two in terms of A, which when you derive something, you could pluck out anything that doesn't have the thing in it. Which, okay, let me show you. You could take the E out, okay? So the flux is going to be equal to E times the integral of dA. And in calculus, you know that the integral is going to be the area under the curve. So this is going to be the area within the Gaussian shape. Okay. And now, what do we know? We know that our Gaussian shape is a circle. Well, it's a sphere, it's a ball of charge, but we want to know, we already know what the area of a ball is, area of a sphere. So we could just plug that into there because we know that the area of a sphere is going to be 4 pi r squared. Okay, so we can rewrite flux is equal to E times 4 pi r squared. Okay, so what does this information tell us? This information tells us that we're going to find the charge that it's inside over epsilon naught. Okay, so by saying that, by multiplying the electrical field to the area, we're going to find the charge of the inside shape. Epsilon naught is just an electric constant. So that's all you need to know. Okay, now this problem wants to find the electric field, which means that we need to solve for E. So E is going to be equal to, well, before I do that, let me just write this is equal to Q inside epsilon naught, right? Divide E 4 pi r squared by 4 pi r squared. We want to isolate E because we want to find E. By dividing a fraction, it's the same as multiplying it by the reciprocal. So instead of dividing this whole fraction by 4 pi r squared, we can multiply it by the reciprocal, which is 1 over 4 pi r squared. Okay, so now you can cross this out. You have E is equal to Q inside over epsilon naught 4 pi r squared. Okay, this is good stuff, all right? Because the next thing you want to know is you want to recall that Ke, the constant, is going to be equal 1 over 4 pi epsilon naught. Okay, when you know this, you can multiply 4 pi epsilon naught on both sides. You get 4 pi epsilon naught Ke equals 1. With this, you could multiply to here and then cancel the 4 pi epsilon naught out. So you get Ke is equal to Q inside 4 pi epsilon naught Ke over epsilon naught 4 pi r squared. Okay, so we can now cancel 4 pi, cancel 4 pi, cancel epsilon naught, cancel epsilon naught. You're left with E is equal to Q inside Ke over radius squared. Now this is useful information, so we're just gonna circle it. Moving on, we want to find what Q inside is. We want to find what the charge inside this shape is. So I'm gonna remove all of this stuff to create more space. Okay. So what is Q inside? Q inside, the charge inside, you need to understand that to find the charge inside, you're gonna have to find the volume of this shape. We're just gonna call it little volume of this shape. You're going to multiply it by the volume density, volume charge density. So volume charge density. Okay, so what is the little volume? The little volume would be just the volume of our little Gaussian shape. So it's going to be, because our shape is a sphere, volume of a sphere is 4 over 3 pi r cubed. And now volume charge density, it's going to be the volume of the whole ball, but you're going to divide that by the charge. Okay, so it's going to be the charge over 4 pi, and instead of r, it's going to be the length from the center to the outer circle, which we have it as a. So it's going to be 4 pi a cubed. Okay, now with this, we can cross out some stuff. We can cross out 4 thirds pi. So let's do that. 4 thirds pi, cross that out. We're left with this, which is Q inside is equal to QR cubed here over a cube. So this thingy can be plugged in here now. So let's do it. E is going to be equal QR cubed over a cubed Ke, all that divided by r squared. Okay, multiplying a fraction is the same thing as, no, dividing a fraction is the same thing as multiplying the reciprocal. So we can rewrite this thingy to to be equal to QR cubed over A cubed KE multiplied by the reciprocal of this. Reciprocal of r squared is 1 over r squared. Okay, now that we have this, we could cancel some things out because we have r cubed over here and r squared over here. Cancel r squared out, you're left with r. Okay, so E is equal to QR KE over A cubed. Once you have this beautiful piece of information, you're going to circle it because this is just magical. Now all you need to do left is just to plug in what we know. Okay, so let me make space for us to plug in what we know. Let's remove this part over here. Okay, so we know that we don't know E because we're trying to solve for E. We know that Q, big Q, is going to be 10, so the charge is 10, times R. R is our little r here. R of our Gaussian shape is going to be 2. KE is our constant, over A, which is this, the length, 6 cubed. So calculate that, whip out our calculator. We have 10 times 2 over 6 cube. You get 5 over 54. So 5 over 54, which you can write as a decimal to be 0.0925925929, which it's a lot, so we're just going to keep it as 0.09 KE newtons per coulomb. And this would be your answer.